We continue with our study of Lyapunov exponents, and now what we are going to do is compute all Lyapunov exponents. To do that, we must first understand something called the Gram-Schmidt SCHMIDT orthogonalization, which you may have studied, but for completeness I will tell you what it is. So let us say you are given a set of vectors v1, v2, v3 up to vn. You want to get a set of orthonormal vectors. Orthonormal u1, u2 up to un. The way to do it is you say u1 is equal to v1 by the norm of v1. So that's the first one. Then you say for k greater than equal to 2, you say wk is equal to vk minus the sum from r equal to 1 to k minus 1 uk. I will write it like this. Think of it as a dot product. I don't mean uk, I mean ur vk. So that's a number times ur. What I will show you the geometrical interpretation of this soon, and then we say uk is equal to wk divided by the norm of wk. So let me show you the geometrical interpretation of this. The geometrical interpretation is, let's say you are given two vectors, one like this, that's v1, one like this, that's v2. What you do is you first divide this by its magnitude and get this one, let us say. So that's u1. The next thing you do is you take the component of this vector along u1. So what you do is, well, that's wrong. What I mean is you take the component of this vector along u1. That's what I mean. So u1 dot with v2 times u1 is this vector here. So when you subtract it, you are left with the perpendicular part, that is this, and then this you divide by its magnitude and you get something unit norm. So what happens is, starting from these vectors, this one and this one, you end up with this set of orthogonal vectors, this one and this one, and they are of unit magnitude. Okay, so in MATLAB this is done through something called the QR decomposition, which is numerically better behaved. So given a matrix like this, let us say this is A, when we say QR equals QR of A, then we get a matrix Q like this, which has orthonormal columns, and we get a matrix R like this, which is upper triangular. So that is R. Okay, well, I wrote small letters, so I get small q and small r. There is only one problem: these diagonal elements may not be positive. We want them to be positive, so we will pull out the diagonal elements and make them positive for some reasons that I will clarify soon. Okay, so the QR decomposition up to a sign difference is given easily in MATLAB by the the Gram-Schmidt orthogonalization up to a sign difference is given in MATLAB by the QR decomposition. This is numerically better behaved. If you have a very tall rectangular matrix like this, you know, the number of columns is much smaller than the number of rows, then you can put a comma 0 here to get a thin QR decomposition. In our case, that will not be necessary. Alright, so let me show you the QR decomposition in MATLAB first. So here we are in MATLAB. I have done some calculations. I will be using these later, so let's not worry about those. Let us say A is equal to rand 2. Let me do rand 3 to demonstrate. Okay, so here is a 3 by 3 matrix. Then what I say is U1 is equal to A1. Well, let me do it like this. Let me say V1 is equal to A first column, V2 is equal to A second column, and V3 is equal to A third column. Okay, so these are the 3 columns. You can see that they are matching. So here you see this 0.3404, this 5853 is here. Similarly, 7513, 2551, they are here, and so on. So I've defined them. Then I say U1 is equal to V1 by the norm of V1. So I've got that. Then I say W2 is equal to V2 minus V2 transpose times U1 times U1. So that's W2. Then I say U2 is equal to W2 by the norm of W2. So that's another one. And then I say W3 is equal to V3 minus V3 transpose times U1 times U1 minus V3 transpose times U2 times U2. Okay, and then I say U3 is equal to W3 by the norm of W3. I hope you agree that I have done the QR decomposition. What I will call it is Q1 is equal to, I will write U1, U2, U3. This is my orthonormal basis. Okay, now let me say QR is equal to QR of A. Okay, and then to compare, what I will do is I will take Q1 and little q and put them side by side. And I hope you will agree that you see the first column of Q1 which I got from Gram-Schmidt and the first column of little q that I got from QR, they are really the same except for a sign difference. The second one, the sign matches. The third one, the sign matches. But basically QR gives you the same result. I am more interested in this matrix R that I got from QR. Here, QR, R is a diagonal matrix. It is, sorry, not diagonal, it's upper triangular. I will be interested in the diagonal elements, but in the magnitudes of those diagonal elements. Alright, let's go back to theory here. So we are continuing with the Duffing equation. So there is a time there. Q dot is equal to f of qt written in first order form. Then we consider another q, which is q plus xi. So q plus xi dot is equal to f of qt plus df xi plus order xi square. As we have done before, we will neglect this. So we have this one then cancels. These two are equal. That is called the variational equation. Then what we will do is we want how many Lyapunov exponents are there. So for the Duffing we actually have v equals x dot and, or well, let me write x dot equals v and v dot equals x minus x cube minus cv plus f sine omega t. So that's my Duffing equation. Let me erase this so that it does not distract you. Right, so that's the Duffing equation now. So there, it's two-dimensional, right? So there are two rates of divergence. Let me remind you that you have x here, x dot here, and time here. You have some trajectory, which I will draw in yellow. So here is some initial condition and some trajectory. I will think of variations, so one here and one here, and these variations will evolve. And so if you think of a circle of variations over here, that will eventually become an ellipse of variations around that point. So it will have a direction of most rapid growth, and then another direction of the next most rapid growth, which may actually be shrinking. It doesn't matter. So circles will go to ellipses because this is linear. Spheres will go to ellipsoids, and we are interested in the principal radii. Okay, so now to calculate that, what we do here is as follows. We start with two random directions. Okay, xi1, xi2, they are perpendicular, they are unit norm, but the first one is random, so the second one is determined by that. In 3D, two of them are random, and then the third one is determined, and so on, and they are perpendicular. So when I integrate forward, what happens is that the xi1 sort of grows in the direction of largest growth, and the xi2 is also becoming parallel to that. It is also moving towards that direction of largest growth. What we will do is we will let the xi1 evolve in its direction as it will. So we will just normalize that but not mess with its direction. And with this one, what we will do is we will throw out the component that is in this direction and take the component that is not in that direction, and then this is going to be the second largest growth rate. Okay, this is why we are going to use the QR decomposition. So each time we will integrate forward like this by time t, then we will normalize this one to here. This one we will cut out the component that is along that one and then normalize to here, and then this one, which I will now mark with this violet color, this is going to be our new direction, which is different from that one, unit norm, and then we will integrate by t, and then we will get something else, and we will do Gram-Schmidt again, and each time we will keep track of the multiplying factor in both directions. That is why we need the diagonal elements of R in the QR decomposition. Okay, back to MATLAB. So here we are in MATLAB now, and this is the program I have. So let me show you this program. Duffing 2. What I have done is I have calculated the Jacobian, that D. So let me show you that now. So here we are. We have, so you see this one now, let's call this F1, let's call this F2. Del F1 del X, del F1 del V. Let me extend this a bit. Del F2 del X, del F2 del V. Okay, so that is why we have 0, 1, 1 minus 3x square and minus c. That's what we have in MATLAB here. 0, 1, 1 minus 3x square and minus c. But now I actually have a 6-dimensional state vector. So I have, 3 and 4 elements are the xi1, and 5 and 6 elements are the xi2. Each one just gets multiplied by the Jacobian matrix. The perpendicularness or orthonormality between xi1 and xi2 are going to be maintained separately. Okay, so that's Duffing 2. LLE is a program that you have already seen for the largest Lyapunov exponent. Here I have BLE for both Lyapunov exponents. So you see the initial condition is 6 by 1. But then what I do is I take the 3, 4 and the 5, 6 part and I put them side by side. I do QR and now I have normalized them. I put the normal vectors back. That is the direction. Okay. If you think about the direct sign convention, it won't matter, right? Because it seems to be indeterminate by a sign. So sometimes it is plus and sometimes it is minus, but because it is linear, the evolution rate does not matter. All right, here is omega. Now I am going to store two numbers each time. So Z is 0 to n. I have 2 rows and n columns. And then what I do is I do this n times. I integrate through one period each time with the initial condition y0, which I have defined here, and then will redefine later. Okay, I will redefine it. So then after the simulation, I pull out the end state. I take the end components of that end state. I do QR and I reassign normalized perpendicular components to the initial condition y0. I don't change y1 and y2 because those are my original dynamic variables. You should be familiar with that. Then I send that initial condition back to Duffing 2. And meanwhile, what I do is I store the diagonal elements of R. So from QR, I get a Q that goes into the initial condition vector. I also get an R from which I store the diagonal part. So you should see what is the diagonal part. Here there is R. If I say diagonal R, then I will just get this one, and this one in a column matrix. Okay, so that's diagonal R. Okay, so that's my program. And then what I have done is I have run this because it takes a bit of time. In the last lecture, it was taking some time. So I have run this for 1,000 steps. Okay. After running it for 1,000 steps, because R is sometimes positive and sometimes negative, and I am interested in the absolute value, that is why I have taken the absolute value. After taking the absolute value, I have taken the log, and that log now I am going to plot. Since I have 1,000 points, I have n from 1 to 1,000. Then what I am doing is I am plotting the running average of the first one and the running average of the second one. The first one is going to be the largest Lyapunov exponent. The second one is going to be the second largest Lyapunov exponent. If I have 3 states, then I have to do this with 3, and you will do that later in some assignment. Okay. So now let me give this plot command and you will see something. So here is the plot command and here is the figure, and you can see this blue is the largest Lyapunov exponent. It is settling at some value like this, which is what we had seen earlier also, something like 0.8, right? Little bit below, little bit above. So it's settling to that. And here is the other one which is settling to a large negative value, something like minus 2.9. What is even more interesting is that these two pictures seem to be quite anti-symmetric about some mean. So that is a special feature of this system which I will now show you. So what I will do is I will do my other plot command, which is the sum of Z. Sum is done column wise. So basically what I am getting is the sum of the two diagonal elements of R for each integration period. Okay, so when I do that, you find it looks very jagged, but actually if you look at the vertical axis, you will realize 2.094395 is common to all of them. There is actually no difference. It's just a constant. What is this number? Well, we can understand that if we go back to this equation here. So you may be familiar with the idea of divergence from your study of fluid mechanics, but what it means is how much volume is coming out or going in or something like that into a unit volume. And so if we look at the divergence of this flow, what we have is del F1 del x plus del F2 del V, which is really the sum of the diagonal elements. This is the time varying part, but that does not appear in the divergence of the flow. Okay, so what happens here is the divergence of F, the vector, is equal to minus C. What that means is that a volume is equal to volume 0 times e to the power minus C t. Okay, so since we are mapping forward by time capital T is 2 pi over omega. So what we have is e to the power minus C capital T. Then we are taking the log of that, and so we are getting minus C capital T. Okay, that's what we are getting. So we come here back to MATLAB and we say C is, we know C is 0.2 and omega is 0.6. So minus 0.2 times 2 times pi by 0.6. That's the number format long. And we have 2.0943951. Now if you look at this graph, you will see minus 2.0943951. You see, so it is perfectly accurate, and that is because we have 8 places, so that's how accurate it is. 8 places. What 8 places? Here, this 8 places. Okay, in our numerical integration. All right. So the estimates of the Lyapunov exponents are actually fairly accurate, because for that we have to do the average like this of a fluctuating quantity. So the estimates are fairly accurate, right? I think the first decimal place is correct and the second one I'm not sure, and if I, instead of 1,000 steps, if I do 10,000 steps, it will be approximately 3 times more accurate, square root of 10, right? So that's one part. But because the sum of it happens to be constant, we are able to check at least some part of the numerical integration, and that is what we do in this curve here. And the fact that it is essentially constant up to the specified integration accuracy given to ODE 45, it means that we probably have not made any very bad errors. Let me show you something else. So when we look at these Lyapunov estimates, Lyapunov exponent estimates, I have one Lyapunov exponent that is greater than 0. That means there is chaos. There is exponential divergence of nearby trajectories. We have another Lyapunov exponent that is less than 0. That means something is being attractive. Something is attracting something. The sum of the Lyapunov exponents is negative. That means that volumes in phase space are shrinking. Okay, they are shrinking exponentially. You will notice that neither of the two Lyapunov exponents is 0. That is because we have a non-autonomous system. So it is because we have, well, it is because we have this term here. It's non-autonomous. If it was autonomous, then one Lyapunov exponent would have to be 0. So we will later study something called the Lorentz system, which has 3 states, and it is autonomous. So when it is autonomous, when you have an autonomous system, I am going to again pretend I'm going to show it with 2 axes only, right? Because this is time. I hope you don't mind, but think that this is 3. Imagine that it is 3. So here I have this trajectory. Now I can actually think of a perturbation in this direction and in this direction. I'm thinking of it as 2, right? But you must understand that when we perturb the trajectory, so when we think about it in phase space, which is possible for an autonomous system, then we can draw a different picture. So we can draw this picture. So here we can have x1, x2 and x3, and then we can have a trajectory that is going round and round in this phase space, and then we can think of perturbations here 3 directions. Okay, and then what happens is we have a sphere of initial conditions, and by the time we come here it becomes maybe a highly elongated ellipsoid. So this sphere becomes an ellipsoid because we have linearized our equations. The dynamics of the growth and change of shape of the sphere and the growth of the change of orientation of the sphere, that is all a linear differential equation. So the size of the ellipsoid doesn't really matter. We keep normalizing it to keep our numerical calculations well behaved. Alright, so it can get very, very long in this direction compared to this direction. It doesn't matter, but because it is an autonomous system, one perturbation is along the trajectory itself. We can start it at this point instead of this point, and it will be a little bit ahead in time, and after a very long time it will still be just an equal amount ahead in time. Okay, so it may stretch a little, compress a little, stretch a little, compress a little, but it's not going to go infinitely far away because we are in some bounded region of phase space. And so what will happen is, for an autonomous system, one Lyapunov exponent will be 0 if there is a persistent non-zero trajectory, right? So of course, if in 3D what happens is everything just goes to one fixed point, then all volumes are shrinking and nothing is 0. There's no, that's not possible. All those distances will also shrink and go to 0 along this trajectory when we come here. But if there is a trajectory that sort of goes round and round in 3D and so on, and keeps going, in that case, one Lyapunov exponent must be 0. I hope you have also realized, I have not said this explicitly, I should say it now, is that in 2D, if you have something that comes like this, it can never cross over, right? So in 2D, there is too much constraint. In 2D autonomous, there is too much constraint, so no chaos. You can't have very irregular orbits, right? It's only when it can come out and go round and round and do funny things that you have chaos. That is why for autonomous systems, you need 3D phase space. Minimum 3, can be more. So 3 or more. Then for chaos, you need that. And in 2D, you need excitation, external excitation. That is what we have in Duffing. So non-autonomous, you can have chaos. That is the minimum number of dimensions you need. That is the minimum amount of geometrical dimensionality you need for trajectories to really start showing complex behavior. Now, if you think of fluid splashing, then you realize that there's a very large dimensionality over there, which is why turbulence is such a terribly difficult problem, and approaches to it are different. Our approaches are for lower dimensional systems. Okay, that's all for today. Thank you.